Julian Venkum. I gave last week's talk about the structure of the Witwatersrand. That was given from Dunedin in the South Island in New Zealand the day after we'd been actually on a genuine placer deposit. I'm currently in Kaikoura at the moment. Kaikoura is known geologically for a geological event. You're probably used to the idea of error bars on geology events, but Kaikoura's event happened at 2 minutes after midnight on the 14th of November in 2016, when it had a 7.8 earthquake, and the wave cut platform out on the point here was raised about a meter, and it's now above sea level. So that's the primary geological thing about Kaikoura. I'm in.
We lost him, Neil.
I can't hear him anymore.
Yeah. Okay. Let's give it a minute, and then we might kick on anyway, Neil.
Okay.
Okay, Neil, I suggest we kick on. You're a well-known gold geologist, and maybe just give us a brief synopsis of your background in 1 minute to 2 minutes and what you're going to talk about. I think that's probably more efficient. Yeah, thank you. Thanks, everyone.
I'm Neil Phillips. I'm based in Melbourne now, and that's where this is coming from. I spent a few years in the University of Witwatersrand, living on the Central Rand and West Rand group in the 80s. And I guess most of my life has been spent working on different gold deposit types: slate belt gold, Phanerozoic, Archean greenstone, and the Witwatersrand. I've been working with a number of different colleagues on Wits gold over the last few years, and some of that's coming out as publications, some of it as talks and so forth. So what I want to do tonight is sort of follow up Dave Craw and follow up Julian's. Dave on the sort of placers and New Zealand modern analogues, possible analogues, Julian on the structure, compiling and summarising a large amount of literature on Witwatersrand structure. I'm going to go back a little bit and not actually join all the dots at the end of this, sort of leave those a bit open, but talk about metamorphic waters or metamorphic fluids. They're linked to gold. A lot of what I say applies to Phanerozoic deposits, Archean deposits, and so forth. So it's metamorphic principles, if you like. So I see this really as a contribution to some hydrothermal puzzles, some of those very relevant to South Africa. For example, can we really move fluids through solid rocks? There'll be a number of people here who shudder, like Caitlin Jones and Alex Kisters and so forth, Steve McCourt, and say, yes, of course you can. We've known that for a while. And there's others who might puzzle and say, well, how does it happen? And I guess the other one is, can we get gold into solution in nature? And again, you get the same separation of it's clear to some, not to others. Now, the interesting thing is Des Pretorius, obviously a very well-known person in the Joburg geological community, said a very emphatic no to both of those. Now, I'll be a little more fair and say that he published that quite clearly in the 60s, 70s, and into the 80s. So I'm going back a bit, but it's that he was not silly. He was simply reflecting the understanding at his time that these type of things might not happen. And he used that, and obviously a very influential person, and not the sort of person people would very easily sort of argue against or move on beyond those. Now, at the same time, I want to touch on two other puzzles. One is, can we identify a possible source for 53,000 tonnes and more gold that we've mined from the Witwatersrand? And secondly, or fourthly, can we use uniformitarian analogues rather than ad hoc models. Now, I'll explain what I mean by ad hoc there. Ad hoc's when one has a model, and we'll call it the Placer model in 1900 perhaps, and Young and others do some studies. The gold is all Hackley. It's all clearly secondary to any petrographer. And so one maintains the Placer model by making an ad hoc change and saying it's already mobilised. Now, that may be correct. I'm not saying it's right or wrong, but it's ad hoc in the sense that there was no evidence, or there still is no evidence for that remobilisation. So it's an ad hoc addition. It'd be nicer to have uniformitarian things and say, well, I see this happening there. And of course, that is a strength of the straight Placer model if it matches things like Dave Craw's talk last week. So I want to look at the metamorphic waters or fluids, and I'll flip-flop between those two terms and explain the difference in a moment. What are they? How do they form, and why are they important in nature and gold? And I'll tackle three terms. Hydrothermal is not something to be scared of. It's simply hot water. And the importance of that in economic geology and ore formation worldwide is really nicely explained in Lawrence Robb's textbook, where, and it's 15 years old now, but it's got a really neat part on why waters work so well, what are chemical properties of waters that make them great for transporting different sorts of metals, and why do a lot of the metals around the world rely on heated water. This term fluids, generally speaking, at the temperatures we can survive in, we understand what steam is. Its gas is H2O. We understand what water is. It's liquid H2O. When we go to 370 and a bit more degrees centigrade, the physical differences between those two merge, and there's no difference. It's all one phase. And that we call that a fluid, to make sure we're not trying to guess that it's one or t'other. It's not one or t'other. It's just one phase with common properties. So that's a fluid. It's a safer term, if you like, a more generic one, saying I'm not quite sure of the temperatures. We'll just call it a fluid because I'm not making a call either way. And the other one is aqueous. Aqueous fluids simply mean based on water. And an awful lot of what we do in geology, economic geology, is water-based. It might be water with salt in it, but we're not talking about CO2-based or cyanide-based or things like that. So aqueous fluids there. Now, water in the crust, and this relates back to that comment about Des Pretorius and others at the time. There was a revolution in the 1970s, particularly in UK and probably North America. And to a large extent, I see and others see Bill Fife as being a key player there. And interestingly, I mentioned that he was a Dunedin boy from New Zealand, but he did quite a lot of that work in England at Manchester, and then he went to Canada and spent the rest of his life there. Very interesting, very wide coverage of Higgins and metamorphic petrology, wrote textbooks and wrote a lovely book on fluids in the Earth's crust in the 1970s. I'd say really essential reading as far as I'm concerned. And that one other person I'm going to mention is John Ferry. And I think I see one or two people online who probably suffered through weeks and weeks of John Ferry's work when I was lecturing at Wits, maybe Rob Burnett, I'm not sure. But John Ferry worked at Johns Hopkins in Maryland. He's retired in the last few years and worked living in California, but he made huge contributions to how the metamorphic reactions and processes work to give us the different types of fluids. Bill Fife was saying, hey, look at that on your left, look at that on your right. As metamorphic grade changes, a large amount of fluid must be involved. And then John Ferry said, well, here are some of the reactions of where it's coming from, where it's going. And key people in South Africa early on, who actually in some ways stood up and said, well, hey, these are important. Russell Myers, Jonathan Law, Julian Verncombe, and I probably should add John Ridley there. He was in Zimbabwe at the time and went to the West, but again, added a lot in the fluids area. Now, stepping right out and looking at the globe as a whole, people talk about 5 different end members for fluids. One can fine tune those and make more if you want, but meteoric is rainwater. Seawater we're familiar with, diagenetic or connate waters, basinal brines, they're the type of things that get buried in sedimentary sequences. Magmatic waters, you'll hear more from John Clemens about those next week, but if you've got a granite magma, it will take into the magma a certain amount of H2O. As you cool it down and it goes into a feldspar quartz rock, we call a granite, then that water has to go off somewhere. And the last one's metamorphic, which I'm going to talk more about. Seawater there, that's easy. Rainwater there, that's easy. That can go down many kilometres. There's no problem, rain going down several kilometres. There's clear evidence it does in some places, 2 kilometres at least. And connate waters, those are buried with the sediments. So if you think of a sloppy, sandy or silty rock, it's the water that goes with that in between the grains. And we'll talk about that in a moment. We've got our metamorphic waters here, and we've got our magmatic waters. This is an important difference between diagenesis or diagenetic stage and metamorphic stage. And I think this is where, and again, I'm not being critical of people in the past, whether it be Young in 1917, Grattan in 1930, or Des Pretorius or others. We simply didn't know these things at the time. And people like Grattan in particular, they were arguing a lot about the fluids going through at this diagenetic stage. Now they do move through those rocks. This is a siltstone on the left with lithic fragments. We know a huge amount about that from the petroleum people because it's so important to them, but it's not what we're talking about here today. On the right is the metamorphic stage. We have essentially no gaps. They're both really thin sections of a few millimetres. The diagenetic stage has porosity, or if you like, holes between the grains, can be up to 20%. So that's a large amount of waters trapped in there. And the metamorphic rocks, hard rock, if you like, can be down to 0 or close to 0. No gaps or holes in it. And if you want an example of what the right-hand metamorphic stage is, let's just think of a quartzite, a central rand group upper Wits quartzite, just as an example, a hard rock. The diagenetic stage is a bit like a sponge in the kitchen sink, where when you heat it, you squeeze it, you deform it, you use gravity on top of it, you can squeeze out the waters there. And that happens in sedimentary basins. That's not today's talk. So diagenesis to metamorphic environment, it's the loss of porosity there. So the trapped waters are driven out. Now those trapped waters could be lake waters if your sediment formed in a non-marine environment, or they could more commonly be marine waters if it's a marine rock trapping these early waters. And that water will be expelled, and with it, it'll take chlorine and everything else. So there can be quite saline waters that go off. And once all that's happened, our metamorphic story starts now. How much water in these solid rocks? Well, it does vary. It varies a bit between, is it the Boyson Shale in the middle of the upper Wits, or is it at one of the quartzites somewhere near there? There'll be different answers to this. Now, we're not talking about the rocks are wet because I left them in the bath last night, or that type of thing where we drive it off just on a kitchen hot plate. We're talking about heating it more. This does happen in the laboratory. And for the older people who've worked in igneous petrology a lot, we used to have our H2O plus and our H2O minus and quote those loss on ignitions. But we're interested in that latter one. I'm working towards how much water in these solid rocks. When we heat these to 500 and beyond, we access or release the structural water. This is water in the structure of the minerals. I'll come back to that. It's released when the mineral breaks down, and the key ones, the easy ones, are the different clay types, the micas and chlorite. We'll focus a bit more on the chlorite later on, but it's those minerals that have this essential water in their structure. Kaolinite's an easy one to start with. It's a relatively simple clay. Certainly the formula is simple, Al2Si2O5OH4, but we can rearrange that and just arrange it perhaps a bit more the way an analytical chemist might. Al2O3 is molecule, 2SiO2, 2H2O, and you can start seeing the familiar oxides there and the water part. And there's a kaolinite structure, which I certainly won't be trying to describe, but it's got the different things in it, and the O's and H's, Si's and Al's are key parts of that. They're not just floating around making it wet. So back to our different molecules there, we can work out the percentage by weight of the water by looking at the molecular weight of the aluminium, the silicon, and the water, multiply 18 by 2, and we get 36. That's 36 over 266, 13% water in kaolinite. Now, that's quite a staggering number, actually. I mean, that means we've got proper kaolinite. It's just normal mineral in a display case, and it's got 13% water in the structure. And for lots of minerals, that is actually quite a high number. But it's not negotiable. You can't take that out. You can't just sort of heat it off and say, well, I've now got kaolinite without that water. It's non-negotiable. It's part of the kaolinite structure. It's almost like saying, well, I'll take the aluminium out and I'll call it kaolinite. Well, it's not kaolinite. It's something else. It's a different mineral. It's critical for the mineral structure of kaolinite. And likewise, I could do the same with micas and chlorite. So how much water in solid rocks? Now, going around the same approach, kaolinite, we get, as I said, about 13. Chlorites vary a bit because their Fe and Mg variability. We'll say 10%, weight percent water. Hornblende and amphibole 2. And a lot of these well-known minerals, pyroxenes, quartz, pledge, clays, garnet, it's close to zero. It is zero. There's no structural water there. And one might look at a trend there and say, well, hey, I recognise these are our sort of weathering and low temperature minerals with a lot, medium temperature and high temperature with none. And that's exactly right. As temperature goes up, we tend to move towards less hydrous mineral assemblages. So I want to look at the green schist to amphibolite facies transition, and we'll see why we sort of pick on that. Not all metamorphic facies transitions are equal and equally relevant. This is pressure on this axis, temperature on here up to 1,000. Right across the low pressure, we're looking at contact aureoles, not talking about that today. Right up here, we're looking at the very high pressure, often subduction related, eclogite, blue schist, where you get minerals like lawsonite, glaucophane and so forth, prehnite, pumpelliite, Dave Craw had in New Zealand. Not talking about that. This is just a standard, perhaps Barrovian type progression from green schist rocks to amphibolite to granulite. And the thing you notice about most of these facies names is they're named after mineral or minerals in mafic rocks, rocks of basalt or dolerite or gabbro if you like, but we'll call it basaltic type compositions. Green schist after the chlorite, amphibolite after the hornblende, blue schist, glaucophane, lawsonite, eclogite, and so forth. So it's mafic rocks that define these. Now, doing the same calculation as we did for kaolinite, but using chlorite and hornblende, we can say my green schist facies rock might have 50% chlorite, and that chlorite has 10% water, and so therefore that rock has 5% water, assuming no other minerals have OH in them. And then you do the same for the hornblende up here, and you get 1%, and you look at the granulite and say, I've got clinopyroxene, orthopyroxene, quartz, and plagioclase, and it's close to zero. So that's the type of thing Bill Fife looked at, and we're talking back in the 70s, and said, well, there's nothing too controversial about that, the numbers and all that. You can calculate it, or you can grow the rocks in the lab and do a loss on ignition. The tricky part, and he was prodding people to make them think about it, was where is that? Where's that gone? Because that's a large amount of water. I know it's only 2 or 3%, but you multiply it out to metamorphic terrain. These are vast amounts of water trapped at the early stage sometime back here, but released by the time you get to granulite facies. So let's go and look at that in nature. We could do it in the Otago region of South Island, New Zealand, where Dave Craw was talking about the other 2 weeks ago. I'm not going to use there right now. I'll come back to it later, but he's got prehnite pumpelliite facies about 100 degrees and up to garnet oligoclase type of plagioclase at 600. So over that 500 degree spread, he's got quite hydrous prehnite pumpelliite, lots of water, and quite anhydrous garnet plagioclase rocks. So we're seeing exactly what we predict, loss of H2O as we go up metamorphic grade. Right at the moment, I'm a little more interested in this example, partly because of its scale. We're looking at there at Boston, we're looking at Northeast USA. This is the state of Maine, and this is the Appalachian Mountains. They've mapped in a large amount of amphibolite facies with some granulite here, and the green around the outside of that is green schist facies. So there will be a lot of places there that there'll be a mappable isograd between green schist and amphibolite facies, and it's hundreds of kilometres in extent. So this is a very large metamorphic terrain, and you're looking at hundreds of kilometres here of rock that has gone through that transition. Where is the water that might have been involved? The other interesting thing is, as an aside really, is this south central Maine is where John Ferry spent an awful lot of his time looking at the well-exposed rocks there and really trying to understand the changes that were taking place across the isograds that people had been mapping, and finding things like the biotite isograd was a decarbonation reaction. Now that's a little bit non-intuitive, and desulfidation reactions and things like that. That's all published, and as I said, quite a lot of my students have suffered day after day of reading those papers and chatting about it. But yeah, very interesting stuff. So there's a substantial loss of water in this green schist amphibolite granulite. Let's look at how it forms, particularly. I won't talk too much about how the fluids moves and where it goes. That each of those could be a week, or in fact a whole series of talks like this. A lot of it's published. There's still speculation, of course, but I want to look at the formed part. And that's what we're looking at. Same diagram, pressure here, temperature across the bottom. It's the green schist to amphibolite, and this, of course, is semi-quantitative only. It's a textbook undergraduate type of diagram, and we can do a little bit better than that and tighten it up, which we're going to do in a moment. But the type of questions is, what's that gap? Forget this axis at the moment, but is that gap hundreds of degrees, or is it half a degree, or whatever? How does the change from one of those to the other sort of take place? They're the main minerals: chlorite, green schist facies, maybe a bit of actinolite, quartz, albite, and other things. We'll come to carbonate and sulfides later. Hornblende plage, the classic amphibolite facies assemblage in mafic rocks. And as Bill Fife said, look at that, 5% H2O, look at that, perhaps 1%. There has to be a fluid that goes off. I can't see it, I can't track it, but it basically is just mass balance. Well, there's a green schist facies rock. The green is chlorite. The high relief colour here is carbonate. The white is quartz, perhaps a little bit of albite, and then there's iron oxides here. Now, people like, well, Spike and John Bristow and one or two others will look at that and say, but that's an apophytic igneous texture, and they are exactly right. The patterns of the pyroxenes, the patterns of the feldspars around that, so an ophitic texture here, but this is a green schist. It's retained. You've got a pseudomorphous texture there after the ophitic texture, but it's completely metamorphic minerals now. There's no pyroxenes, no original plagioclases. And as we go upgrade, we've got hornblende here, plagioclase there. This example's probably got a bit more biotite than I'd normally select. And this one here, all of this is hornblende on the right, and hornblende, and this is plagioclase. Just look there, and you see the plagioclase twinning. So we've got hornblende, plagioclase, the classic amphibolite facies diagnostic assemblage. Little bit of quartz, and there'll be some ilmenite there too. Not too much of this, but they're really interesting and important diagrams and approaches to give some numbers and help us understand this. It's a pseudosection, which is really a bit of a phase diagram for a particular rock type. You don't need to know what that rock type is, except we happen to know it's close to a basalt. I know there's lots of different types of basalts, but it will be a particular one, and we can do it for other ones if we want to. And these are just sodium, calcium, iron, magnesium, aluminium, silica, water with quartz present and water. Pressure on this axis, not so important because everything is roughly parallel to it. Temperature here, very important across the bottom. We're in that 400 to 500 range. We've got classic green schist facies assemblages over there with it'll be chlorite, lots and lots of chlorite there. And we've got classic amphibolite hornblende plage here, and there won't be much chlorite here, but it's hornblende plage is the key part for amphibolite facies. So this is our boundary, and we've now got numbers to it, which we've been able to calculate using thermodynamics. And you can see there that first we hit 1% of the rock by mass has been lost as water, 2% has been lost, 3% has been lost, 4% has been lost. So somewhere between here on the left and there on the right, we've lost 3, 4, maybe 5% weight of the rock in water going off somehow, technically fluid. And you look at that and say, okay, that's for metamorphic terrain. That's now starting to be quite a lot. The other parts of this is that change takes place over 10 or 20, maybe 30 degrees. And that's important because if we were walking across here and we were mapping green schist facies rocks in the morning, we stopped for lunch and then headed off, continued on and walked to amphibolite facies in the afternoon, that's feasible. If instead this took place over 800 degrees, we might have many, many days walk between our green schist and amphibolite, and we'd say, I don't really know where that change was. It just slowly changed over hundreds of degrees. So it doesn't. It changes over quite a narrow interval. It's involved with all the water loss, or most of the water loss, and that makes it a mappable isograde. That's why it works. That's why mapping these isogrades has worked for the last, since 1920s or before. Because they are water release events and they give you quite a change from a chlorite-rich green schist to a hornblende plage amphibolite. One more diagram. We've now got rid of the pressure and said we'll just do it at 5 kilobars, 550 to 400, the same temperature range on the vertical. And we're looking at two things here. We're looking at green schist down here in the lighter coloured, amphibolite facies in the darker colour, hornblende plage, chlorite-rich rocks with a bit of carbonate here now. And the fluid that is released is not pure water anymore because there's carbonate in these assemblages. It's now a mix of water and CO2. Now that mix of water and CO2 aren't two different fluids coming, one from the left-hand side and one from the right. They are coming off together as a mixed water CO2 fluid, and the mixing or the ratio between the two is determined by the phase relations here. And we can see, without sort of splitting hairs, somewhere around that 1 to 4, 1 to 3 ratio between CO2 and water. So it's a CO2 water mix. And over here, it's simply saying that as we move up temperature, suddenly we get a lot of release of water here and goes on there. So it's not a rapid progression. It's all to do with changes from lots of chlorite to lots of amphibole, therefore lots of water going off. So capturing that, the fluids evolved at 450 degrees, plus or minus, CO2, 20, 25%, and there can be variation. I suppose the important part about the CO2, it's not 0 and it's not 100. And so we must think, how do you get somewhere in between? What gives you this 20 thing, whether it's in Victoria, in the Paleozoic, or it's in the quartz veins in the Wits or quartz veins in Barberton? Something is dictating that, and it's not a random mixing between two end members poured into a pot and then stirred up. It's something's buffering that, and it's the mineral assemblage. If there's a little bit of pyrite, which is common but not ubiquitous, we can generate some H2S in the same fluid. and we won't have any chlorine. It won't be a saline fluid because there's no chlorine in any of the minerals we've been dealing with. Now, if this happened to be an evaporite, all bets are off. It's something completely different, but we're not dealing with evaporites in any of these things I'm talking about. So it's a low salinity fluid, and that becomes important with the base metals. Now, the fluid migration one is a tricky one, and it could be a subject for a whole evening or much more. And again, Alex Kisters and Caitlin Jones talked about this quite a bit. Julian certainly touched on it. Sorry, the first two in the series 2 years in 2022, Julian last week. Over on the left there's a granite. Over on the right, there's the outer contact aureole. This is the inner contact aureole. It's cordierite hornfels. So it's been heated to 500, maybe 600 degrees. We can see trace of bedding there. We can see this cross bedding. We can see sandy areas. We can see shaly areas. And we can trace that out to the right-hand side and say, well, these are generated by contact metamorphism of shales, which we see, and they must have lost 3 or 4% H2O in going from the shale out on the right to a cordierite hornfels. And the cordierite hornfels has got cordierite, quartz, feldspars, maybe a little bit of biotite, but not much else. So essentially close to anhydrous, but not completely so. A different example here of fluids. And the point about this is that you ask me, well, how did the fluid get out from everywhere around here when this was all chlorite to now go to cordierite and K feldspar? And the answer is I don't know. And I don't think it's going to be these things. These are relatively recent cracks, either when the road cutting was made or sometime through unloading. But it's got to leave from every single grain across here and be heading off. And so it's not something we can really replicate, but we can. There's been quite a lot of science on how fluids move through those and get out. But it is a really difficult thing for many people to grasp when structural geologists talk about, oh, fluids have been moving through here or through there. Metamorphic petrologists and structural geologists tend to come from the other way and say, well, it really has to, because look what you've got there, 1% or less. Look what you've got here, 4 or 5%. It has to have lost, and you can do your tests in the chemical lab. A slightly different example here. This is a magazine. The theme there was fluids in metamorphism. And the dark, it's the opposite way around actually, but fluids coming in. The dark are granulite facies rocks. The light are amphibolite facies rocks. And you can see that's coming on whole fracture network. And the scale there is quite large when I remove the snow. And there's our mate sort of doing the field work in Antarctic. So this is big scale post-metamorphic fluids coming in, but working through the rock. And you can't walk up to that, and you can't find cracks. No holes, no cavities, no cracks. But I think it's pretty obvious that fluids have moved through that rock when it was hard, the hard rock I talk about. Okay, we're going to move to Southern Africa, South Africa, Table Mountain on the left. A group of Stelly students there, and we are looking down on Cape Town. And there's a box there in gold that is I'm going to just have to move my thing. We've got a box there that's 5 kilometres by 4 over downtown Cape Town. I'll put about a 1 kilometre by 1 kilometre there. And it's very interesting to speculate if my chlorite-bearing assemblages with 5% water, or a kilometre by kilometre by kilometre, how much water might we be involved there if we could, which we can't, if we could ever get it out. And that's a cubic metre. And so what we're talking about there in the Cape Town example would be 1,000 of these lined up, then 1,000 rows of those across the ground, and stacked 1,000 high. And then we're saying, but only 4% of that is water, because if it was a chlorite schist. But you suddenly look at that and you say, well, there's 1 cubic kilometre of water, 1 cubic kilometre of rock, and we're looking at literally many, many megalitres. And I guess the question I leave, sort of half in fun, but it's a really interesting question, is that 1 cubic kilometre, how long would that supply a city of 5 million people like Cape Town or Melbourne or Sydney? And you can work out from the daily consumption, it's not just a few minutes or a few hours. It's a very interesting example of how much of this metamorphic fluid there is, and the difficulty of trying to explain, well, how did it all get out? Okay, we're going to add, make this a little more complex. We're going to add gold in, and we're going to add a bit of sulfur in, and we're going to recap that green schist facies amphibolite boundary or transition. We know it happens in the Archean. It can be mapped in the Barberton Greenstone Belt, in parts of the Yilgarn, many other places. It can happen in other continents, and there's nothing super special about it. The magic part is that it sweeps through the whole rock, and I'll talk more about that, but you're not just getting 1 or 2 grains giving up a little bit of water. That the whole reaction sweeps right through and changes every bit of chlorite, involves it in reactions with dolomites and other carbonates and actinolites and so forth. And the neat thing about the gold is any gold there will tend to go into the fluid at the time it forms. That fluid doesn't form and then head off somewhere else to go and get gold. The moment that metamorphic fluid forms, it is gold bearing, if there's gold there to start with. We introduced this term devolatilization, and that's not trying to be too smart or anything. It's really just saying it's much more than dehydration. We're involving decarbonation. That's our carbonates going to calcium in something else, be it amphiboles or feldspars, and desulfidation. So that could be the breakdown of pyrite to pyrrhotite or breakdown of pyrite to iron in silicate form. And those 3 all happen together. And it's probably John Ferry's work that I think has been most influential to see how those things are combined from the nature or the field point of view. And Roger Power's work very much on the thermodynamics, bringing it together and saying, yes, we can explain that in theory, we can see it in the field. So that's this devolatilization. On the left, our green schist facies rock with green chlorite. On the right, our hornblende amphibolite facies rock. Somewhere around 400 to 450, the transition takes place. We might be losing, and I do flip-flop between 4 and 5% volatiles there, but I'm not going to argue that. The key thing to remember is I have chosen a certain rock type, and if that was a quartzite, it'd be no volatiles as it goes to a quartzite. So not every rock works like this, but good common garden mafic rocks do if they've got a bit of carbonate alteration and chlorite. You get complete conversion. It's not a case that 1 or 2 grains out of all of these go to hornblende. That whole rock, including the textures, go over to something completely different. And that means there's access to all the gold. And I'll talk about that gold. That gold is parts per billion level. These are not lumps. They're not nuggets. They're not even grains of gold. They're just completely diagrammatic representation of gold at the parts per billion level, and so probably an atom here, an atom there, and really not much at all. And as we go from left to right, the fluid has to go off, and that's water H2S, and it will be very accommodating of taking gold into solution as a bisulfide complex. The gold goes into fluids, and that fluid is gold bearing from day one. It's the day it forms in that transition, it's gold bearing. And we could look at this way here. This is the boundary there. It's a bit diagrammatic, but it sweeps across, converting more and more of the green on the left chlorite into hornblende plage. And as it does, it just passes over and sweeps up and picks up all these atoms of gold here and there. And they go with the water, with the CO2 and with the H2S into the fluid that heads off. So the gold atoms go into the fluid, and the fluid is gold bearing from day one. They're the key parts of this process and why it's so effective. And a simpler version of that would be pretty comfortable with people perhaps thinking about Barberton, Western Australia, Abitibi Belt, Victorian Goldfield, New Zealand, and so forth. Or you can turn it around this way. which is a bit more realistic in the Earth's crust. The isograde sweeps up through the above mafic green schist facies rock, and you get hornblende plage. Now that's fine. One might say, well, we'll prove it. And coming from a different angle, Dave Craw, Rob Kerrich will be known to, the late Rob Kerrich will be known to a lot of people as a real giant in the field of gold, based in Canada, and interestingly, spent part of his early career with Bill Fife at London, Ontario. And Ian Pitcairn's in Stockholm at the moment. This was his PhD, I believe, with a number of people with different skills, sort of saying, A, we'll look at the field area and set up a really neat project, and B, we need fantastic analytical lab, which they had in Saskatchewan, thanks to Rob Kerrich and Ian's work, and we need a fantastic analytical lab to tackle this and tackle it seriously. So we're back there in South Island, very much where Dave was talking about 2 weeks ago. We're back there to this diagram of 100 degrees, the really low metamorphic grade, up to 500 and 600 degrees, and water being lost as we go through there. Now, it's not going to be just water. That's a simplification. 100, 200, they just put numbers to these and say, okay, we're going up temperature. They collected a whole lot of samples, 124. They analysed the major elements and 50 trace elements. And they said, well, what's happening as we go from 100 degrees to 600 degrees? They're getting a significant variation in things like gold, arsenic, antimony, mercury, and a few others. They got 1% or more loss of water, but they got no loss of base metals. So we're now seeing a separation between everything. It's not everything going up. It's quite selective. Base metals are staying. Gold and gold-related elements, which we'd recognise from many gold deposits, are going down. And they put 2 or 3 of these diagrams. Now, these are log scales, so don't sort of worry too much. It looks flat. It's actually quite a significant loss of gold here and here. Temperature going up as we go down the diagram. Mercury, very clear loss of mercury with metamorphic grade increase, and a decrease in silver as metamorphic grade goes up. And so for gold, they just publish these figures of 0.56 parts per billion gold. That's pretty low actually, and 0.2. So you've lost more than 50% of the gold just going up there. And keep in mind, with all due respect to New Zealand and the New Zealand work, New Zealand, South Island, it's not the world's biggest gold deposit we're talking about here. These are probably not the right rocks. It's just illustrating that what we were predicting is exactly the way it works. We lose gold and gold-related elements going up metamorphic grade in these rocks, and we lose those related elements, but not base metals. There's the base metal work, and we see we don't lose copper, zinc, or lead. It's a different picture. So base metals left behind because these are low salinity, and gold and gold-related elements taken away. So we swing back to the issue of is there enough gold? Is there enough gold in the world for this 53,000 tonnes from the Vits and quite a lot more that's still there, we assume? And we go back to this slab sitting on Cape Town. It's 4 by 5 kilometres, so 20 square kilometres. We'll make it 1 kilometre thick for the calculations. And I'm going to say there's no gold deposits down there. I don't know that for sure, but let's make an assumption there's no gold deposits. There's no quartz veins with gold and so forth. So the gold contributed by grains is 0. But there's background gold in all these rocks, and we're going to say 1 to 2 ppb. And that 1 to 2 ppb will calculate out to 100 tonnes of gold or 3 million ounces in a 1 kilometre slab of that size. None of it you'll be able to see, none of it you'll be able to extract. There's virtually no chance of ever finding a gold atom in that, but you're looking at a 3 million ounce resource. No big deal sitting in Cape Town. No one's going to do anything with that. But the principle that just that small part there of part of the Cape could be hundreds of kilometres in the Appalachians or other parts of Southern Africa now start saying we've got a vast resource of gold here at this PPB level if we can get it out. And the other part of the story, of course, is that we do have a way to get it out, and that way is this isograd forming a fluid, forming it being gold bearing the moment it forms, and then it's up to structural geos and other people to take that off on their structures and go up and form gold deposits somewhere above, hopefully. And it won't always work. So to recap, these are processes that are global. They're not restricted to one part. They can happen through most of Earth's history across different continents. The real magic part of it is that that isograd sweeps through 100% of the rock and everything is converted from essentially low-grade assemblage to high-grade assemblage, and the gold is in the fluid as it forms. To make this work, we need heat energy or metamorphism. Well, that's fairly obvious to drive it from green schist to amphibolite, high temperature. In my examples, and I think it's pretty important, chlorite and a fair amount of chlorite would be really helpful, and chlorites in mafic rocks or grey wackies as the source material. A little bit of carbonate is essential for this story. It will be there in lots of sequences, of course, but it won't be in all of them. A little bit of pyrite is essential, and it won't be in everything, but it's not a great sort of stretch to have it in quite a few of them. And this some parts per level gold, I don't think is any big deal. I mean, Ian Petkin showed that there's parts per billion level gold in lots and lots of different rock types, and it's just a sort of crustal background average. So I'm going to wind up there. I'm not going to join the dots and say, where does this go for the Wits, or where does it go for Barberton, or where does it go for Kalgoorlie or so forth? That's a story for another day or discussion, but I hope we can sort of throw in here, it helps to understand this metamorphic devolatilization process that people talk about, throw the words around. It's a crustal process, green schist facies to amphibolite. Doesn't have to be that, but it's a very good candidate in many cases. Happens through time, continents, and metamorphic events, and you can dissolve gold and remove it. And it won't always work. It won't work if you've got no sulfite, no pyrite there. It won't work without carbonates and so forth. You need chloride. So, but it's not too much special pleading to say we've got those conditions happening in a large number of places around the world. I'll wind up there. Some of this is in my sort of more recent book on how these gold deposits form, but there's also a paper there, happy to send to anyone, that's with Roger Powell on the sort of really sort of first putting it together, the whole metamorphic devolatilization model with a few numbers to it. So Julian, I'll finish there, and I guess I'm happy to take questions.
Thanks, Neil. That was excellent. Julian, are you back online? You can drive.
Yeah, I've got my link back. Normally at this stage, the chair tells you something about the chats and repeats the chat questions. I'm unfortunately trapped here because my chats have gone to an AI system related to a rosemary, and I'm sorry, I don't understand what's happened.
Okay. Yeah, not to worry, but I think you just drive the questions that get asked. People can also put up their hands or open their mics and join the fray. Don't be
Well,
shy.
certainly, I think people need to. I mean, I'll just start by iterating how the important point from Neil's talk is that the gold is being accessed in the rock at the same time as the fluid is being driven off. And that moves us away from models that many structural geologists were presenting in the past, where we saw the gold being the fluid generated in one place and then it traveled and it obtained the gold somewhere else. I see that as quite a major step, at least in understanding of the process. I have to turn it over to you guys because I can't read any chats, and somebody's got to come in and ask a question.
Okay.
Can I
Let's
start the question, please, Julian? Keith here, Keith Kenyon.
okay, just speak into your mic, Keith. Go for it.
Can you hear me?
Yeah, I can hear you now.
My question is, Neil, one of the elements you left out of the discussion, and one that concerns me, and I've got two examples, one from the Petersburg Greenstone Belt and one from your consort in Barberton. The Greenstone gold deposit, the one at Petersburg, is a Snowman's Drift #3 gold mine. The entire vein which was mapped as chlorite quartz, is actually tourmaline quartz. And all around consort, I've got lots of thin sections with tourmaline in. What is the role of boron in these systems?
Okay, I'll just backtrack for everyone. Your observation that you get tourmaline in these deposits is absolutely correct, and it's really important. Tourmaline's one of the three minerals that's got essential boron in it, and therefore what Keith is doing is he's saying, I see tourmaline over there. What's that telling us about boron? Well, the interesting thing is on a periodic table, boron's number 3 or 4 is it? And you look and say, that's sort of way different from all these gold, mercury, antimony, arsenic, selenium, tellurium, and so forth. But the key property of electronegativity, boron, is very similar to all of those, and so bonds and works well in a reduced sulfur fluid. Base metals don't, but boron does. So it's one of those things where chemistry suddenly says, hey, I mean, this really does make sense where the boron fits in there, whereas I never would have thought just looking quickly at the periodic table. So again, that's written up in that paper. Electronegativity is the embracing or synthesizing little bit of chemistry that helps understand why those elements are related to gold and why other ones aren't.
Thanks, Neil. Good talk, by the way. Excellent talk.
Thank you.
And Spike, I mean, you're very quiet today, or do you want to join in?
Not really. It's a nice talk and nicely presented and uncontentious.
Okay. That sounds very boring, Neil.
That's a first. That's a first for my CV.
Yeah. Okay. Anyone else out there?
John, it's Andy Clay.
Hi, Andy. Go for it.
Hi, Neil.
Hi, Andy.
Very interesting talk, and you know, from my days back in the Wits, and Des Pretorius was my supervisor, so the comments that you made earlier on are go straight to home here. What I was interested in is to what extent the chemistry of the water systems that you're talking about, we can learn more actually from the oil and gas guys, because the oil and gas guys are dealing with water-driven environments and big basins, etc., which generally don't go higher than amphibolite facies, just simply because that destroys all the hydrocarbons. But they're talking about big water systems, not all of which is connate either. I'm not sure if you've considered that.
Certainly, if I wanted to understand how fluids move around, particularly at that diagenetic stage when the rocks are like the sponge analogy, I'd always go to the petroleum literature because they're miles ahead. When you get to the hard rock, my Central Rand quartzite analogy, they've actually got much less interest because it's not going to it's not going to let petroleum flow at all if it's there and so forth. So yeah, it depends which part of the story you're interested in. On the chemistry, it's a slightly different chemistry, and a lot of their waters tend to be or can be saline and slightly different composition because they have a different origin. They might be buried seawater. They might be buried seawater that's evolved through reaction, become even more saline. So there's a bit of a difference there.
But then, Neil, based on that, are we convinced that the Wits gold is a mixed hydrothermal and sedimentary origin system?
Well, that's joining a lot more dots than I joined, but I'd say there's no question about the sedimentary system for the shales, the conglomerates, the quartzites, and my own bias is the gold and the gold-related elements are hydrothermal. Perhaps the key there is the carbon tells us quite a lot, and you hinted about the higher temperatures for petroleum people. Regardless of what we think that carbon is in the Wits, it's probably there either right at the start or very early on during the diagenetic stage.
Yeah.
And if so, it's gone through metamorphism of 350, maybe 400 degrees in the Wits. So it's actually gone way beyond the anthracite stage to whatever we see today. And I think it would just be, it's just completely improbable that you can look through something much hotter than anthracite and still go back and be talking about filaments and all those things. I don't think any of those textures are original. They're all metamorphic textures. And it doesn't really matter whether you want it to be alkyl mats or fly-spec carbon or oil and petroleum. It's all been metamorphosed. I'd say it was virtually inescapable that that's been to 350 or 400 degrees. I don't think anyone's talked about it being post-metamorphic.
Thanks very much for your great talk. Thanks for answering my question.
All right.
We've got a question from Linda Ejeri. Well, in fact, 3 questions, some of which might be a gift and an opportunity for Neil to advertise his book. But why and how, so this is going to the other end, why and how does the gold drop out from solution? So in other words, how do we form the deposits? Why are greenstones such good traps? And then the third one is, why are the magnetic horizons in the lower Witwatersrand not mineralized where other parts are? So that's only a couple of lectures for you, Neil.
Well, I think the magnetic contorted beds, all the other, we call them BIF or iron-rich shale layers, but in the Westrand group, lower Wits, are good. And I think I'd tackle it this way and say, let's go and look at those where they do have gold in Barberton, in Western Australia and so forth, and see what they look like. Now, most of what you see in Western Australia, the Bandit 9 formations, have no gold. And where they do, they are very limited in structurally complex areas and often poorly outcropping. And you look at Barberton and there's a lot of iron-rich rocks that don't contain gold. So it's not going to be spread out in every iron-rich rock you find. Where would I look if I was looking for gold in the lower Wits iron-rich things? Well, clearly under the some of the better suburbs of Johannesburg would be a really good start. And you say, well, I'm completely serious. It's not a commercially viable, but that's exactly where it's likely to be. And I would take a bet that no one's really looked systematically there and drilled it out to show that there isn't any. And of course, there'll be other places around the basin. So it's not explored. It's probably going to be a tricky one anyhow. But it's not fair to just go and have a quick look in one of the suburbs and say, well, I don't see any here. It's like taking a quick look at a conglomerate saying it's barren, therefore there's no gold in conglomerates. So just not explored. Why
There's
are
one
key
more
in
question
greenstone?
from Mark,
No, hang on.
where
We've got
he's asking where the fluids end up. So what happens to the fluid that's not helped form your favorite gold deposit?
I think there'd be examples. Okay, I'm postulating that there's millions and millions of litres coming out in the Appalachians from my the little metamorphic map I had of Northeast USA. Where does that go? Well, I would guess that would move up through the structures, probably come out at the surface. It's not going to come out as pure metamorphic waters at 350 or anything. It's going to just mix on the way up with whatever else there is, basinal brines, rainwater, maybe sea if it's in the ocean. I don't think you're going to find them as pure metamorphic waters in a lot of places near the surface, but that'll just be the vast amount that comes out as springs, soaks along faults and so forth. And I just might add that some of John Ferry's work, I think he was talking about these going to 15 kilometres depth. So we're actually talking about the metamorphic waters in a large hydrothermal systems there and moving up through the crust.
Yes,
I'll tackle that one if you like.
Yeah, and you've got Julian, you've got Clyde Mallison, who was sort of also in the queue, and then John Clemens as well.
I'll just tackle Linda's if that's all right.
Go
Why and
for
how
it.
does the gold solution? Yes, as Julian said, I mean, that's explained quite a lot in the book and some papers, which I can supply afterwards if it's helpful. Part of the greenstone story, obviously, is the structure, and there's two really good talks on that in the 2022 series, and it's well worth looking at those from a bit more of the structural point of view and some alteration. But also the key things to get gold out of solution, it works really well if you've got iron-rich rocks, and it works really well if you've got carbon as a reducing agent. And of course, one can hunt around and find both of those to varying degrees in Barberton, in Kalgoorlie, and of course in the Wits. They are different rock types, but they're the same chemistry. Carbon acts as carbon, whether it's in the fig tree or it's in the carbon leader or Kalgoorlie. So it's a bit of chemistry and it's a bit of structure there for that question. I don't have the other question you talked about, Clive Mallison and someone else.
Yeah. Hi, it's Clyde here. I don't know if you can hear me.
Yes, I can.
Yeah, first of all, thanks, Neil. It was a brilliant talk. I love it when people not resort, but use first principles of mass balance, basically. And so having been a mill superintendent early in my career, I'm very familiar with mass balancing. Where did the copper go? How much is on the tailing pump and how much? So mass balancing always appeals to me. And I think you put that across exceptionally well. And just to echo Julian's thing about the fluids and the gold being generated in situ, as it were, I think if people can imagine it from a tax point of view, it's like VAT as opposed to personal tax. Everyone contributes. So I just thought I'd leave you with that.
I might use that next time. I like that.
Yeah, thanks very much for the talk. Really enjoyed it. Thank you.
And I think over to John if we can.
John Clemens sorry.
John Clemens.
Yeah, I'm a bit out of focus there. Now, here I am. Yes, thanks, Neil. I echo the others in saying great talk and lots of things to learn and think about. One of the things you mentioned was that it was pretty hard to imagine how during progressive metamorphism, where we're beyond this simple loss of interstitial water that you get during compaction and in sedimentary rocks and that sort of thing. When we get into the real metamorphic side of things, it becomes a little harder to imagine how you get rid of that water that has to have been gotten rid of, as you point out. So I think there must be some other people in the audience here who know about what happens during metamorphic reactions and recrystallization and that sort of thing. But I'm not an expert in that side of things, but from my point of view, grain boundaries are moving around all over the place during progressive metamorphism. So you have a porosity, transient porosity developing during all that process. And clearly H2O molecules and other volatile components can be moving along features like the grain boundaries. This is on a small scale within the rock. On a larger scale, it then becomes more interesting to figure out where that fluid that's moving around like that on a small scale, how it actually gets out of the whole rock system. And I think there's probably no alternative to structures such as fractures. But again, these are transient because the whole system's being metamorphosed and recrystallized. New minerals are growing, reactions are occurring. And maybe that's why it's all covered up and we don't see the evidence of that. I might talk just a very small amount about that sort of thing in the higher temperature regime when I give my talk later on.
Okay, well, I mean, sorry, I didn't want to cut you off.
No, I was basically saying a comment on that. Yeah.
Okay, well, the first thing is you use the transient, completely and utterly agree. You use the grain boundaries importance, yes, completely agree there. We don't understand that fully, but colleagues of ours like Steve Cox and so forth worked on that quite a long while ago and said it's the grain boundaries. Eventually it has to amalgamate to more than just the grain boundaries into things that will become shear zones, and we'll pass over to the structural guys then. But and the other thing is earthquakes, and a number of people have talked about earthquakes, and that's the transient part that you get earthquakes. A little bit happens, then it goes back. A little bit happens, it goes back. So a lot of those are tied in there. There's quite a lot on it. I'm really just quoting from other people and happy to go along with that sort of best attempt.
Yeah. Well, I guess my point is that people shouldn't be left with the feeling that there's some weird magic going on. I think we do know the sorts of things that are happening there. It's not something that it looks impossible, but it isn't. As you point out,
Yeah.
the rocks have done it, and we do know some of the physical principles and crystallographic things that are allowing these migrations of fluid to occur on the small scale. To me, the bigger puzzle is how that feeds into the larger things, like, as you mentioned, the shear zones, fractures, etc. So, but that has to be the way they move. Fluids don't seep through rocks slowly up porosities for very long. They do that on the small. But, as Julian would probably say, that it would be ridiculous to ask a fluid to do that over kilometers, upwards.
That's exactly right. Yeah, completely agree.
June Cowan's got his hand up, and it'd be good if June came on because I suspect that he's got a comment on exactly this material.
Do I?
June,
Really?
well done.
You caught me by surprise. Neil, the question that I have for you is that you mentioned sulfides, and I'm of the opinion that a lot of these sulfide deposits that are called VMS or, syn volcanic deposits, which are, most of the time right next to gold deposits, like in the Superior province. Let's just assume that they are not, right? They just form just like gold deposits because you can't tell the difference morphologically. How do you think they form if you assume that they're epigenetic deposits?
How do I answer this? Can I just say this is not on my duty statement?
Yeah, but I mean,
look. I mean, they are in the same province. You get gold-only deposits, what I've been talking about, and you get your classic VMSs in Canada. I wouldn't say they're exactly close together often, but that's a matter of scale, I guess. I think they're quite different for the simple reason I'd explain the gold-only deposits, be it the Fitz, be it Carlin, be it Kalgoorlie, be it Barberton, by low salinity fluids carrying all those elements and gold, but not base metals. And I'd go and say, whatever you want the other ones, the VMSs, to do, I'd be seeing those as seawater or evolved seawater or something that's highly saline. As a chemist, that that sort of two end members makes sense to me. On the timing, obviously there's been good discussion on the epigenetic, syngenetic. I don't actually have strong knowledge or views on that, and I don't. It's probably not a 1 minute question either.
I think you should.
So, well, we might invite you to give a talk here some later time on just
I
that.
think people in Perth are sort of well aware of this debate, and it's probably pretty new to Southern Africa, and it's something that the OGG group may want to look at, and to get June to talk about that work. I see that Spike's got his hand up. Can we go over to Spike?
Go for it, Spike.
I can tackle Andy Clays while we wait, if you like.
Sorry, I had my microphone off. One of the things that always intrigued me is the formation of amygdales and geodes. You know, you've got a solid basalt, its grade's very low, and yet they can fill up with quartz with the most detailed and intricate internal structure, either horizontal, radial, or horizontal. And then, so the water must be able to flow through what it really is a solid rock. Somehow gets through there, and maybe grain boundaries are the things, but they're not particularly, you know, these basalts, amygdaloidal basalts are not particularly granular, and yet fluids go through there. The other thing that I just want to comment on is the banded iron formations and the absence of mineralized gold, of mineralization in those banded iron formations. You know, Richard Fillion employed a student once, it's actually a French guy, and they put him on to did a systematic gold survey on a banded iron formation in the footwall of the Val Reef out there at Clarkstorp. And he did a, you know, normal sort of rock chip sampling across this whole fold belt. It was one of those areas where the rocks are very steeply dipping. And they didn't find any gold at all, nothing. So, you know, I've always wondered why, especially, you know, with the Barneycoat type model where you have thrust zones, these thrust faults that move through the rock mass and cause the alteration of, you know, formation of gold deposits, supposedly, but they don't in the case of the Lowervits. So although there's been big thrust faulting and so on in the Lowervits, I'll talk about that when I get my talk, they're unmineralized. So it basically restricts on where the gold has moved to and how it can move. But certainly it's not moving through these major structures if it is moving. So yeah, just 2 comments. Thanks.
Thanks, Spike. Neil and Julian, you carry on. Is anyone else we haven't covered?
Andy Clay, I think.
Andy?
Yeah, I'm actually just commenting on what Spike said. You know, it always amazes me how tightly constrained the mineralization is within the conglomerates. And once you go in the footwall, there's diddly squat, and the same in the hanging wall. So it's very tightly constrained. But equally, Neil, a number of those reefs are specifically shallow marine. So I would have thought that connate water would have been salty and would have had sodium, etc. in it. Your comments?
Yeah. Let's say they were shallow marine. We're not going to argue that. They're buried with salty water. That's absolutely fine. And that, to me, would be the diagenetic stage, where somewhere between when they're soft and sloppy at the marine sediment stage and they're now hard rocks, be they quartzites or whatever, they must have lost all their diagenetic waters by the stuff I was talking about early on, and all the chlorine will go off there. And that's the diagenetic stage. Potentially that could move base metals, but it's probably not really material here. But by the time you get to the metamorphic stage, the chlorine's all disappeared. So yes, it will be saline at the connate water diagenetic stage, but it won't, there's no reason at all why it should be saline at the metamorphic stage, because there's no minerals that have chlorine in their structure, significant chlorine.
No, thanks, Neil.
Is that Terry Spike wishing to come back?
Yep. I just want to ask, Neil might know the answer to this. What are the fluid inclusion compositions look like? I don't know. I don't know any of that work, but presumably there's been a lot done. Are they saline brines or are they made of something else? Low salinity, whatever.
They're a little bit varied. I mean, you might remember, Dieter Horbaugh, but Nicky Robertson did an honours project on the sea reef at Vale Reef, the Vale Reef mine, and looked at that. And that was water, CO2, 350 or something like that. And I think it would be indistinguishable from sort of Kalgoorlie or Barberton or Zimbabwe greenstone gold. It was right in that patch. Then people did calculations and showed, well, that could never, that type of fluid could never transport gold. But I think the calculations were wrong because Anglo at the time were mining sea reef there, the quartz vein, for gold. So clearly the thermo calculations were just wrong, but water CO2 basically. And I can't think of any with good daughter products like you'd get in a porphyry copper or a saline system.
Okay, thanks for that.
There's also some work from Mari Vale that backed that up. Just trying to think, Rainer Klemp did a bit, yeah. And of course, Gillian Brennan's done quite a lot after that. So maybe she's the person to sort of say, is it much broader than I've indicated?
Okay, thanks, Neil. I'll ask Jill.
Okay, I think we've sort of got to the point where we should be thanking Neil for the talk and also for the emphasis that whilst an economic deposit is obviously special because it's economic, often the geological processes are just the same processes that we see in any other terrain. And it's just what are those processes that enhance usually several elements at a time in the rock. And it's normal geology, it's normal igneous petrology, structural geology, metamorphism, those sorts of things. There is nothing special or different about the processes that produce our ore deposits. So thanks to Neil.
Thank you.
Yeah, thank you, Neil. That was excellent. And again, thanks to all the participants for their questions and discussions and your good chairmanship as well, Julian, most appreciated. Just to also remind people.
Sorry, I just lost a link at the beginning.
Okay, no problem. And just to remind everyone that we are going to extend the presentation series. We're going to have another show and book your seats in advance on the 15th of April. And again, that's a Tuesday, and then on Thursday, the 17th of April. And by that time, you should have already booked your seats and paid for them if you want to participate. But thanks to everyone, and enjoy the rest of your day or night if you are the end of the world down in New Zealand. Thanks, Julian. It's been great.
Thank you.
Thanks, John.
Good night.
Okay. Have a good
Cheers.
one. Bye now.